Good morning. In this unit, we're going to talk about applications of discrete distributions to quality control. And this is like an applications of the distributions of the binomial and Poisson that we have explained in previous videos. Okay, so the case study that I'm going to present is the following. Imagine that we have tangerines, and one of the quality problem is the presence of seeds that probably we all have found in some cases. Okay, sometimes we have seeds and this is a problem for the quality. This is something that we don't want to happen. Okay, so then imagine that we have a supermarket that wants to purchase like let's say like 2,000 kilos of tangerines from a supplier. Okay, so we call this like a batch or a lot. Okay, so like a big amount of this product. Okay, so let's imagine that we have this criterion. If less than 1% of the tangerines contain seeds, we are willing to buy the lot in 90% of the cases. Okay, so we consider that less than 1% is like a good quality. If the tangerines are of good quality, we're willing to purchase, we're willing to buy this batch. Okay, so this is why we have like a high percentage for willing to buy. Okay. Then the quality control is to take a sample of n fruits and then count in those n fruits the number of tangerines that contain seeds. Okay, then let's imagine that we put like a criterion that the lot is purchased if the variable x is equal to 0. It means that any of the tangerine contains seeds. Okay, so what we want to compute is the minimum number of the value n, so the minimum sample size. Okay, so we define the random variable as the number of tangerines that contain seeds in the sample of n. Then this random variable ranges from 0 to n, and this is why it is a binomial distribution with parameters n and p. P would be the probability that a tangerine contains seeds. Okay, good. Then we have that the probability to buy the lot if p is less than 1% is equal to 0.9, 90% of probability. And then we apply the probability function for the binomial. Okay, the probability that this function takes exactly value 0. Okay, this is the combinatorial number n chooses 0 multiplied by p powered to 0 multiplied by 1 minus p powered to n. Okay. So at the end, this is equal to 0.9, and then we compute the value n. Here you have the formula, and then we end up with a solution of 11 tangerines, approximately 11 tangerines. Okay, then now this is a second case, so the problem would be the same, but then imagine that we say the lot is purchased if the number of tangerines with seeds is less or equal to 1. Okay, so we admit one tangerine that could contain seeds. So what would be the minimum number of the sample size with this criterion for quality? Okay, so the criterion would be the same. The probability to buy the lot if p is less than 1% would be 90%. Okay, but now this is what is different. The probability that the number of tangerines with seeds to be less or equal to 1 is 90%. Okay, then remember that for x equal to 0, this is the formula that we obtained in the previous slide. For x equal to 1, this is the formula by applying the probability function, and then we'll have to sum. We sum both, and this is equal to 1. Sorry, this is equal to 0.9. So from this equation, we should solve the value n. Okay, this can be solved with iterative methods. Okay, for example, we can program this formula in an Excel spreadsheet, and then we can try different values of n until we reach the solution. And then with this method, we will find that n is equal to 53. Okay, but we can simplify the calculations by approximating the binomial to a Poisson distribution. The Poisson has a single parameter that we call lambda. Lambda is a so if the Poisson and the binomial have the same shape or the same kind of distribution, they will have the same mean. the mean or the average of a Poisson is lambda, and the average of a binomial is n multiplied by p. So the lambda of the Poisson will be n multiplied by p. Okay, so this is a part of the abacus of Poisson, and then we have this condition. We have that the value of the probability, which is 0.9. This is what we put here. Okay, so this is our condition, 0.9. So we go here. This is the probability that we read on the vertical scale. So we place a horizontal line and we cut the curve less or equal to 1. Okay, this condition means that we have to cut the curve less or equal to 1, and then we place this vertical line, and then here we read the value lambda. In this case, the value lambda is approximately 0.52. Okay, so we say that 0.52 is lambda. Lambda is n multiplied by p, which is the sample size multiplied by the probability, which is 1%. So here we solve, and then we divide 0.52 by 0.01, and the solution would be 52. Okay, so we can find that the exact solution, which was 53, is nearly the same solution that we find approximating the binomial with a Poisson, that is like a more straightforward method. Okay. Well, so generally speaking, so we have in these kind of problems that the criterion to accept the batch is that the random variable, okay, x, in this case, the number of defective items in the sample to be higher than c, higher than certain value, okay. This is like a general definition of the problem. So if that happens, the batch is rejected, okay. But if the number of defective items is less or equal than this value, so the batch is accepted. Okay, so the parameters that we need to define the inspection plan is the following. We have to define the sample size, and then we have to find this parameter, which is the maximum number of defective items in the sample to accept the batch. Good. Okay, so here this is the batch that we assume that it's very big. We cannot check the quality of all the items, so we take a random sample. Okay, so we take a sample of size n. In this sample, we check the quality of all items, and then if the number of defective items is bigger than c, the batch is rejected. Otherwise, the batch is accepted. Okay, so then we have the operating characteristic curve of inspection plans, which is something like this. Okay, so according to the probability of defective items in the batch, if this probability is small, okay, the probability to accept the batch has to be high. But if the probability of defective items, or the percentage of defective items in the batch, is high, we are not interested in buying the batch, so this probability has to be low. Okay, so this would be like the range of good batches that correspond to a high probability of willing to be accepted. Okay, so this would be the probability to accept batches of good quality, and this would be like the range of bad batches, and then this would be like the probability to accept batches of bad quality. Okay, well, so this is like the real curves that are obtained when we have like different values of n from 25 to 55 and different values of c, for a value of c equal to 2. Okay, so more or less this is like a generic curve, and this is like the real curve, and you can see how this curve can be adjusted and takes different shapes so that we can choose the curve that is more interesting for our purpose. Okay, so the curve can be adjusted by modifying both parameters of n and c. Okay, and then here I finished this video of applications of discrete distributions to quality control. Thank you for your attention.